Thanks for the introduction and thanks very much for the invitation. So I will do as Philip, I will talk in English, but feel free to post questions in French afterwards, okay? Okay, so I didn't really know what to talk about today, so surrogate models, so I'm going to talk about what I use surrogate models for so far, okay? So just to give you a little bit of context, because this morning we heard radio frequency and then imaging problems, so I'm going to look at the surrogate models here a little bit differently from a different physical viewpoint, maybe from nano-optics perspective. So this means basically that we have structures that are smaller, or features of our optical systems or devices are smaller than the wavelengths. And in the optical regime, in the visible optical regime, then we have kind of nanometer scale, hundreds of nanometers, or smaller structures, features of the structures in photonic devices. Okay, so Philip also started with the same question: what can we use proxy models or surrogate models for? So in the first, I will start to, well, most obvious thing maybe to accelerate very slow simulations. Okay, so this is maybe the most obvious thing what people started at the beginning of deep learning hype to use deep learning models for. Then, of course, also Philip talked about this already, so I'm going to repeat some stuff, I guess. Most of these models are deep learning models that are differentiable. Okay, so we can make use of this differentiability and use this for optimization applications or to solve inverse problems. And I'm going to try to talk a little bit about inverse problems in more detail. And also Philip named this already digital twins, whatever this means. I guess that all of these surrogate models can be kind of seen as digital twin of something. Maybe you have a digital twin of some other digital numerical simulation or so, but yeah, so I don't really, I won't go into details about this term, okay? So I will just stick with the other things. Okay, so the first, maybe most obvious application of a surrogate model could be to accelerate some very slow simulation or some difficult to describe system like an experimental system, okay? And I will stay with nano-optics now, because that's what I probably can talk about. And so usually if you want to describe some nanostructure, so the problem is usually to find the optical properties of this nanostructure or of some nanophotonics device maybe. And what we often do then in the simulation is we discretize the system or structure in some way and obtain some kind of coupled linear system of equations. And then we need to solve this, which can be computationally very expensive, especially if we have a larger device, a larger structure. Okay, so this is basically the main bottleneck in these kind of numerical computations. So the idea would be that we kind of try to accelerate this with a surrogate. Okay, so I will now use this coupled dipole approximation, but in principle we can do this with any computation technique that we use to solve the problem for generating a database. Okay, I will use this coupled dipole approximation because this is very well established and it's a nice physical model. Okay, that's kind of partly at least interpretable, and it can be applied to different scales. So we can do what Philip did this morning. We can really describe scatterers, each scatterer as a dipole or a few effective dipoles, but we can also use a single scatterer and cut it into small pieces, okay? And every piece, every small discretization element must be just smaller than the wavelengths, basically, so that we can have a static approximation, quasi-static approximation, and describe each cell here as a dipole, and then we can solve for complicated nanostructures the optical response also in a coupled dipole approximation. Okay, so it's depicted here. Now the cool thing is that for many physical systems, like free space, but also for layered systems, or for a system where in presence of a large sphere, we can use weave theory, we can actually describe how a point source, like a dipolar source, emits light. You can describe it with a Green's formalism. Okay, you can find a Green's tensor that describes it analytically, and then we can for a coupled simulation with a lot of dipoles, we can just use a linear superposition principle and use the Green's tensor times the dipole moments for all of the dipoles to compose a system to get the field everywhere in space. Okay, and this is pretty cool because basically when we have a description of the dipole moments, okay, self-consistent dipole moments, then we have essentially solves the entire scattering problem, and we can calculate any physical observable just with these low dipole moments. For example, the far-field scattering, polarization scale of the scattering, directional scattering, radiation patterns, near fields, of course. But we can also, in the perturbation approach, calculate nonlinear effects. basically we can really do anything with this. So this is pretty interesting to solve these internal fields, essentially. And so our idea a few years back was that we could use a deep learning surrogate model to predict these internal fields very, very fast, because this is the slow step of the simulation. All the observations, observables that we can calculate later are relatively cheap to calculate. Okay, and this is the coupled dipole approximation specifically is pretty suitable for using in these kind of network approaches, because usually we discretize the structure on a regular cubic mesh, so we can directly use very common network architectures like convolutional networks. Then we have typically a relatively low number of mesh points, maybe a few 10,000 or so. And which is, I think, particularly appealing here is that we need to discretize only the structure. Okay, we don't need to discretize a large domain like in FTDT, for example, or FEM. We really just need to discretize the volume of the source structure. And then we trained a neural network on a large amount of the structures and their simulations. And we found that we could actually pretty accurately predict the internal fields and use them also to calculate other observables, errors in the order of 1 or 2%. Okay, average errors. Peak errors are a bit higher, maybe like 5 to 10% at specific points sometimes. Okay, and the cool thing is that this is about 5 orders of magnitude faster than in the actual simulation. Then we, so this was for binary input data, so the input was just, is there material at some mesh point or is there no material? But we then also showed that it's possible to generalize this to kind of giving a material distribution where every position has the permittivity of the material or not permittivity that is at this location. And also we generalized to multiple wavelengths, multiple incident angles, and arbitrary polarizations. And we found that this actually works even better, contrary to some other deep learning approaches, where often we see that if we generalize the problem too far, it becomes more and more difficult to train a network, at least a small-scale network. But here this worked even better. So I just depict here the training data range in wavelength and material reflective index. So, okay, sorry. And we found that this network actually managed to generalize surprisingly well to larger refractive indexes or larger or shorter wavelengths compared to the training data regime. So we don't really understand why. But we see that modes that are not in the training regime, okay, that do not touch the training regime, they are completely, the network doesn't understand what's happening there. So it seems that it kind of understands how this mode here, these different modes here, how they kind of behave if we go to different materials or different wavelengths. And because we showed the network a so general data structure, it kind of manages here to extrapolate. So this was pretty interesting. And this is importantly, this is really not a physics-informed training approach, so just based on data. Okay. Okay, so this is really just to accelerate simulations, which is probably a little bit boring. Okay, so like 5 years later, I would say, yeah, this is funny, but this is not extremely kind of mind-blowing or so. So I think what is really more interesting using these, especially deep learning surrogate models, is that they are automatically differentiating. So you get any model that you train like this is differentiable, and then you can use these gradients to make funny things. Okay. So for example, of course, you can do gradient optimization. Like we use this here, for example, in meta surface design or kind of scattering, diffractive scattering optics design. And you can also use it to solve quite generally inverse problems. Okay, this is what I'm trying to explain in more detail. So yeah, as I said, the key technique here is called automatic differentiation. Probably most of you are familiar with this, but I will nevertheless give a short introduction to what this means. So very important, automatic differentiation is not symbolic differentiation. Okay, symbolic differentiation is what we learn at school. Basically, all the differentiation rules that we learn at school. So, for example, the polynomial differentiation rules that are here shown in this example. The problem is that if we have a little bit more complicated functions like this soft ReLU activation function, that is quite not so uncommon in deep learning. And in deep learning, then we have usually several layers where we feed the result of former layers into new layers. Then we can very quickly obtain quite sophisticated mathematical formula. And if we need to differentiate it, then now with respect to every parameter of the network model, then we can end up with very complex mathematical equations. And we need to do this for every single parameter of the system in order to be able to train this surrogate model. Okay, so if we have millions of parameters, then this becomes very quite considerable task to solve, and probably just due to its complexity will be not really feasible. Okay, so this is not automatic differentiation. Okay, automatic differentiation is not numerical differentiation. Okay, numerical differentiation is what we usually do on a computer. If we try to solve derivatives numerically, we will approximate this infinitesimal derivative here with a finite division. Okay, so we will just say we evaluate our function at the position and slightly next to the position, like very small this distance next to this position, and then we divide by this position. So actually what we will do is we don't calculate the tangent, which would be the real derivative, but we will calculate some seconds that is very close to this tangent. Okay, so the problem is that we cannot numerically represent infinitesimally so small numbers. So with h needs always to be kind of a finite number, because if we go too small, okay, then we will increase some round of errors, because at some digit we cannot represent smaller changes to equal numbers, and then we will add some round of errors if we have this h too small. On the other hand, if we make it too large, we will basically cut our Taylor series. We will see that we cut off our Taylor series expansion, okay, and then we make this kind of truncation error. And the key message is that we will never be completely error-free here. And if we need to do this for a very nested function, we have a considerable risk of having some error accumulation. Okay, and at the end of this numerical differentiation, we have some quite large numerical errors. Also, we would again need to do this for millions of parameters, okay, separately, and this would take a large time. So this is also practically not really feasible. So this brings me to automatic differentiation. And automatic differentiation is the idea to derive a method which can calculate analytically precise derivatives at a fixed input value. So we don't want the full equation or formula that we can use to evaluate the derivatives everywhere. We just want the derivative value at a specific input x to our function. And the idea of this concept is that while we evaluate our nested input function, our nested forward model, for example, and every single mathematical operation, we don't only perform the mathematical operation like the summation, multiplication, division or so, we also calculate the derivative, but we don't calculate the value of the derivative, we really store the mathematical operation of the derivative, okay, in some kind of computational graph. And then in a second step, so-called backpropagation now, we will apply the chain rule in the backwards path, okay, and compose our derivative chain rule element by chain rule element, basically, from the back to the front of the function, okay? And because we use here all the analytical mathematical formula that are very short, because it's just every single operation, we get actually analytical precision, okay? But only at the evaluation point x that we use in the forward pass, okay? So if we evaluate a function in a different position, then we need to do this again. The second cool thing about this is it's not only very precise, only also if we stop this process, let's say at some intermediate position here, we automatically get also the derivative at this intermediate position. So we get the derivatives at every single intermediate step. So if we have a rational network with 1 million parameters, we need to do this backpropagation from the end to the front through all the 1 million parameters, and at every single step when we perform this chain rule operation here, we have the local partial derivative. Okay, so we have all partial derivatives in one single backpropagation. That's why it's so interesting for deep learning training, because we know all the partial derivatives for all the parameters of the network. Okay, so so in a quick sum up, symbolic differentiation is slow but very stable. Okay, but deep learning applications, at least, it's usually too slow. Then numerically differentiation is very fast usually, but it can become unstable if you have long nested functions. And furthermore, we need to do it too many times for deep learning. Okay, and kind of the goal solution would be automatic differentiation. The only disadvantage is that we need really to implement all of these chain rule operations into an efficient framework. So this is quite a considerable technical task. Okay, but the cool thing is that we need this for deep learning. So the last 10 years or so, all the global big tech players invested really crazy amount of money in the development of these tools, like Google, Facebook, OpenAI, now also Microsoft, and there's really a mature different mature toolkits that do this in a very, very efficient way, also parallelized on GPU. And basically you can choose any of them and you can solve all the tasks that you want with any of them. Okay. So and this is not everything that exists. Okay, so what can we do with this? So I will try to explain how we can solve inverse problems, and specifically on the example of inverse design problems, but this is really very generic, so you can solve any inverse problem with these techniques. For example, quantitative phase imaging may be of interest. I think tomorrow is about imaging, where the goal would be to, from some intensity measurements, to retrieve the complex field or the phase of some wavefront, where we have usually lost some information and there's some ambiguity in these kind of problems. Then that's what I'm going to talk about now, design problems, okay? But for example, we want an optical response of some meta surface, and then the question is, how do we need to design our meta surface to obtain these optical properties? Another example in optics would be, for example, speckle recognition. So there's this funny paper here where they managed with the deep learning neural network to reconstruct the input image that has kind of been transformed into a speckle through a long optical fiber, which then makes it automatically applicated. It's a fiber in the body that you may want to reconstruct the image at the end of the fiber. Yeah, so this is also an example of an inverse problem. Okay, so but what makes these inverse problems so difficult? Okay, let's try to analyze an inverse problem from practical life. Okay, let's say somebody drinks a lot of alcohol and then decides to drive downhill to a mountain bike or so. Then the direct solution would probably, direct consequence would probably some severe head injury or something like this. Now, this is the forward problem. Okay, so this relation is unambiguous and direct. Now, on the other hand, if we see somebody who has some kind of head injury or some severe injury, then the inverse problem would be to understand what happened in order for him to get this injury. Okay, and of course there could be many different causes to this head injury than just driving drunken bike downhill or so. Okay, so this is the typical inverse problem, and this is what Philip talked to this morning about, is ambiguity. Okay, so if the problem is not unambiguous, then we typically call this an inverse problem. Okay, so maybe back to nano-optics, it's a very simple example. Let's say we want to optimize nanoparticle size or so to get a specific optical extinction. And we see here already that for specific region of optical extinction coefficients here, we have several possible lengths of this gold rod here that give the same optical extinction. Okay, now if we want to train directly a model on this, input would be the optical property that we want to inverse design, and the output of this model should be the gold rod length. Okay, then we actually run into a problem during the training of this model, because we will feed into, at some point during the training, we will feed into the model here the same extinction coefficient, but we wanted at some point in the training to predict one of the particle types, and at the other point, for the same input, we wanted to predict a different kind of particle. Okay, and actually we will loop through data during training, so this will go back and forth. Obviously, the training won't be stable, and at some point we will probably converge to some kind of average solution, but which is totally wrong. Okay, totally unstable. So this is just not working. Okay, so we cannot directly train a neural network as a kind of inverse surrogate model. Okay, but the forward problem is basically trivial. Okay, the forward direction is unambiguous, so we can directly train a neural network or probably any other surrogate technique on the forward problem. And the cool thing about at least deep learning neural networks is that they are differentiable proxy models. Okay, so this forward simulator here is differentiable, and then now we can use this differentiability to try to solve this problem in a way that Philip described this morning. Basically, we can do gradient descent optimization. Okay, so we start with a set of solutions, predict the optical response, and now we calculate a fitness function where we measure the error of the predicted optical response with respect to what we actually want to obtain as an ideal design. And now in the second step, so there should be step 2 here, we do the back propagation, calculate gradients of this fitness function here with respect to these the geometry parameters or any other parameters of an inverse problem, and then we change these parameters a little bit, and then we repeat this. Okay, and ideally we will convert to something that minimizes this fitness function and therefore implements the optical response or solves our general inverse problem. Okay, so this can work directly if you have parameterized your system well enough, but this can also go wrong because, unfortunately, at least neural networks are very weak typically at extrapolation. Okay, so if you just train a neural network on any task, this is probably very weak at extrapolating. So this is just an example here, network trained on a polynomial function. You see that as soon as you leave the region of the training data, it completely goes into nowhere and the solution is wrong. And this happens also if you have a complicated parameterization of your inverse problem. For example, a nanostructure, which is parameterized by a top view image, okay, in pixel basis. Then if you apply this gradient descent, you very quickly get these kind of completely pixelated patterns, but which are totally wrong. Okay, if you do simulation, it's completely wrong. And this is because the gradient descent pushes the proxy model into its extrapolation regime, where the proxy model may think that the solution is correct, but in reality it's totally wrong. Okay, but the underlying problem is that we have here this representation of the structures. We have here a non-convex set. Okay, where if we try to interpolate between 2 points, we will leave the set of the actual geometries that make sense. Okay, but we can actually use a second proxy model to solve this problem. Okay, and we can use techniques from generative deep learning. The most simple technique would be an autoencoder. The goal of an autoencoder is that we have a neural network that predicts the exactly same information as we feed into the input. Okay, and it does this by going through a bottleneck layer. And this bottleneck layer is typically called latent space, and we choose it typically that it's very low dimensional. Okay, and now if we do this correctly, this network will, if we train it on supervillains, for example, it will learn to group the same supervillains with similar neural activation functions. Okay? Even images that it didn't see before, it kind of recognizes the features in the images and will activate more or less the same neurons in this bottleneck layer. Okay, but just if we train it stupidly, it will probably don't work. Then probably just every image will be mapped to some position in the latent space. So we need to actually regularize this latent space during the training of this generative model. The first property that we want to obtain is that we want to have a continuous representation. So if you change the latent vector a little bit, it should more or less get the same information. We can do this by adding a random number generator here in the center of this model, which perturbs slightly these latent vectors. And then the network learns that if the latent vector is, it needs to learn that if the latent vector is almost the same, it still may correspond to the same. Okay, and this very simple technique forces the network to group similar images in similar positions in the latent space. However, we can still have these blank spaces where basically the network will generate just noise. The latent representation doesn't correspond to anything meaningful, and we want to close them also. So we want to have actually a complete or kind of compact latent space. And this we can do with a second loss term, the Kullback-Leibler divergence loss, which basically just tries to push all these random distributions around the images towards 0. Okay? And then if we manage to find a good compromise between the different loss terms, pushing them to 0, having a good reconstruction, and having this kind of continuous representation, then we will have a completely populated latent space, where we can continuously interpolate. Okay? And this is what's used for generative deep learning. Okay, and then if you do this correctly, you can actually go from the latent representation that corresponds to this image to the latent representation here. And if you interpolate the latent space, then it will really every single latent vector will correspond to a face that is completely kind of really realistic for us, and not to a superposition of different photos as if we would interpolate in the image space. Okay, we can even isolate regions in the latent vector that correspond to specific features like age or gender or amount of hair or whatever, and then we can just modify a single part of the latent vector and change, for example, the age of a person in these image generation networks. Okay, but back to nanostructures. Now the idea is if we want to regularize the inverse problem, okay? So the idea would be that we train a second proxy network on generating structures, nanostructures, okay? And we want to do this by passing through a compact and smooth latent space. So remember, the problem was that we have here a non-convex set of we cannot interpolate between 2 points. And what this actually means is that the set of these latent parameters here is actually a convex set. So we can now interpolate this latent space between 2 geometries. Every single geometry on the interpolation path will actually correspond to a true geometry from point of view of our database. Okay, so this is what it looks like. If we interpolate an image space, we will actually have superposition of two images, which is not really what we want, okay, because we don't even have grayscale values in our original representation. But if we do the interpolation in the latent space, okay, we see that we can go from one structure here to another structure through a series of really changing, but continuously changing structures, which all look like the structures for our database. Okay, so now we have all the ingredients that we need, so we can actually, instead of directly optimizing the gradients in the pixels of the image, we can now optimize the latent space here, latent space parameters, then translate this latent parameter, latent vector, to an image and calculate optical response. And with back propagation, again, modify the latent. And like this, we stay in a kind of closed loop and remain also in the region of meaningful parameter ranges. Okay, and if we see on this toy program that I showed before, what happens if we do this? We actually get a plausible nanostructure now, which has a almost correct scattering response, and it doesn't, most importantly, doesn't look like it's pixelated pattern here anymore. So latest we applied this here very recently to a problem where we have photonic device here, coupled waveguides, where we deposit a small layer of phase change material that we with a laser can locally write. So we can change like regions of 500 by 500 nanometers here on this thin film, and this modifies the coupling between these waveguides. And so our goal was that we wanted to find the structure here and the geometry of this that we need to write onto this film in order to implement a completely arbitrary unitary transmission matrix, complex transmission. Okay, so the idea was here, like I showed before, that we have a generated model that generates these structures, which are predicted then by a proxy physics proxy model, I would say. And the combination of these two proxies here regularizes the geometry parameterization, first one, and the second one regularizes the inverse form. Okay, and this allowed us actually that we really we could define any unitary transmission matrix for phase and amplitude control at the same time. And this neural approach within a few seconds, it's still iterative, okay, would give us a correct pattern that we need to write onto this phase change material film in order to implement this this transmission, complex transmission. And this would be kind of a really the most basic building block for some optical computation, because actually what we would here perform is like this matrix, complex matrix multiplication of the input amplitudes here with the transmission matrix. Output would correspond to the result of this mathematical operation. Okay, so for the last 5 minutes, I will go back to automatic differentiation and very quickly just draw your attention on the fact that you can not only use this for deep learning models, but you can really do basically any kind of calculation you can implement in these automatic differentiation deep learning frameworks like PyTorch or JAX. Okay, so this is actually used today also for many simulation toolkits without any deep learning in various physics domains. For example, here I found examples in nonlinear physics, in microscopy, quantum chemistry, geophysics, but also in nano-optics, photonics. Okay, so I did a quick research and I found, for example, transfer matrix algorithm implemented in PyTorch, I think, ray tracing, differential ray tracing algorithm. I think there will be actually a presentation after me about this idea. Differentiable FDDT, okay, and RCWA, several differentiable packages. So this is really has arrived now in the scientific community as a tool not only for deep learning but really for doing any kind of computation which afterwards becomes differential, okay, which can be very interesting. So we have experimented the last 1.5 years. We implemented a coupled dipole model within PyTorch. So actually, in addition to just being automatically differentiable, we also mix different types of coupled dipoles, basically. So we can use these dipoles to discretize a nanostructure to have access to the internal fields, for example. But we can also couple the same structures here to effective dipoles or effective models composed of several effective dipoles. We have larger structures, for example. So basically, this Torch GDM package here is a mix of the green static method, so basically discretization of a single nanostructure with effective models based on dipoles, and all of it implemented in PyTorch for automatic differentiation. So, and now just one application that we are currently working on with this is because now we can do any nano-photonic simulation, but in a completely different way. Okay, so the idea was, can we access near-field information? Can we get a physical model for the near-field interactions, but just from far-field observations that we could relatively easily obtain in a lab or microscopy or whatever. So okay, we need some information in near-field we will need, and we say that okay, we claim that we can place two nanoscatters at very known positions in the near field and move them around in the near field, for example, two AFM tips or so. And we also know exactly their scattering response, so we know their polarizability. Okay, and now what we do, we move them around here in the near field. We illuminate them from the far field. We do this with a dipole source, or make it easy because we can use screen tensor approach, but you can decompose any field in dipole fields, for example. So this is not really limiting generality. And then we measure, we say that we can measure intensities in the far field, okay, and several basically you can make some, I don't know, a backfocal plane imaging or something like this and get the intensities in the far field. Now we say that we do all of this in some unknown environment, okay? So we pretend that we don't know the environment, but we, here for this toy drawing, we describe it with some, we say that there are some nanoscatters in the environment, and we make some numerical measurements, okay? Let's say we make a first set of data that could also be microscopy data, where we can move the nanoparticles around purple nanoparticles. And then in the second step, we try to simulate these simulations here, just that we now say we don't know anything about the environment. Okay, so we do this in free space, but we also add a neural network, so we can decompose, because it's linear optics, we can decompose this green sensor into free space plus environment contribution. And we say the environment contribution, we don't know it, but we say it exists, and we try to model it with a neural network. Okay, now we do the simulation. It will be totally wrong, because in the beginning, this is not our actual environment here. But we now say that we calculate the thickness between the simulated far field intensities and our measured far field intensities. And we try to train this neural network by minimizing this difference, the far field observation, simulated far field observation. Okay? So, and actually, already without any further corrections, this works relatively well. I think we moved the particle here on a grid of 7 by 7 positions in the near field. So this is a much higher resolution than the actual probe resolution. Okay, we already get the features, and I guess from what Philip showed this morning, where he said that he didn't need any more physics constraints, and it did already work, that probably by maybe sampling a bit more densely or sampling at more in the far field or something like this, we could make this work better. But our idea was to improve this quality here, that we could, because everything is differentiable, we can also add any other loss function here. We can calculate derivatives of our fields, for example, and we can test if they are valid with respect to the Maxwell's equations or Helmholtz equations here, okay? So we added this physics loss where we tested if the fields that are predicted, the complex fields, which we cannot measure but we can calculate them. So we tested if they are valid within Helmholtz equations, and if there's an error, we try as an additional training target, we minimize this error. And then actually we get almost perfect agreement between the actual environment description here and our trained, learned environment description based on this differentiable simulation toolkit here, where inside this differentiable simulation we train a neural network to the simulations. Okay, so these are preliminary results, but Sophia started writing the paper, so hopefully this will be published sometime soon. And with this, I wrap up my presentation. So I want to, I don't really, I spare me the time of conclusion. I forgot to make a conclusion slide, sorry. But I want to make some publicity for our toolkit. So this talk GDM is almost published. We just respond to the reviews. I hope it will go through. So I think this is relatively mature. We tested it against a lot of cases. I think it's pretty stable. So if you think it's interesting, you're very open about any feedback. Then collaborating with Southampton, we are currently developing a differentiable mean toolkit. So basically, we needed to implement Riccati-Bessel functions in PyTorch because they don't exist. To implement the recurrence relations for this. And this also works already. We're currently, Oscar is trying to write a paper about this. So if you want to act as a beta tester, we are very welcome coming any feedback also. And about the first part of the presentation, the basically inverse problem solving, we published here 2 years ago this tutorial paper. So also a bit of publicity for this. And with this, I would like to thank the contributors or the collaborators that mostly contributed to what I've shown so far here, and of course you for attention. Thank you.